Think about the machines you interact with before lunch: a microwave heating your coffee, a traffic light turning green, your phone blurring a portrait, your bank freezing a weird transaction. They all seem smart, but only 2 of them are actually using artificial intelligence. To spot the difference, we have to define what intelligence actually is. A microwave and a standard traffic light are examples of basic automation. They don't think and they don't learn. They operate entirely on fixed rules. A timer counts down to 0, or a light cycles from red to green every 60 seconds. No matter what is happening in the outside world, these systems follow their preset instructions to produce the exact same outcome every single time. Your phone's portrait mode and that banking fraud alert operate differently. They actively analyze the scene behind your friend or the unusual location of a credit card swipe and make a real-time decision. That is true artificial intelligence. Confusing basic automation with the processing power of AI makes it difficult to see the logic currently making decisions for us. To understand the modern world, we have to look at how these machines actually learn. True AI separates itself from preset rules because it has the ability to adapt to unpredictable situations. In the early days of computing, scientists operated mainframes that were restricted by strict, rigid programming. If a situation wasn't explicitly coded into the system, the machine couldn't process it. This diagram maps out machine learning, the modern engine driving AI today. Instead of relying on hard-coded instructions, these 3 approaches allow systems to learn by analyzing vast amounts of data. Shifting a machine's primary diet from fixed rules to raw data is the exact mechanism that transforms a simple, repeating tool into an intelligent system. This flowchart shows the most common approach: supervised learning. It starts on the left with predefined, labeled data. Each shape is provided with a corresponding name tag, giving the machine a set of verified examples to study. During the model training phase, the algorithm analyzes these examples to identify the specific traits, like the number of sides or angles, that connect a specific input to its verified label. Once trained, the model can look at new, unlabeled information and use its knowledge of those internal patterns to identify the shapes and assign the correct labels. This logic allows an email filter to categorize messages as spam based on previous examples, and it's how a smartphone camera identifies which pixels belong to a face versus the background. Supervised learning is highly effective for categorization, but it requires humans to provide millions of labeled examples before the machine can make its first prediction. This graphic illustrates unsupervised learning. Here, the machine is fed raw data on the left without any pre-assigned labels or human guidance. Without labels to follow, the algorithm explores the data independently. It loops through the information to detect hidden structures, similarities, or anomalies on its own. Based entirely on the structural patterns it discovers, the system organizes comparable objects into these distinct clusters on the right. E-commerce platforms use this method to group shopping habits. By analyzing thousands of purchases, the algorithm clusters your preferences with similar users to recommend what you might want next. This independence allows machines to discover patterns in vast datasets that are too complex for humans to categorize manually. This diagram breaks down reinforcement learning. It relies on a continuous loop between an agent and its environment, where the machine learns through trial and error. The machine takes an action and observes the result. It receives a reward for a successful move or a penalty for a failure, which it uses to update its understanding of the current state. The algorithm repeats this process millions of times. By constantly modifying its decisions to maximize its total reward, it eventually identifies the most efficient path to the correct output. This feedback loop is how AI learns to master games like chess or Go, and how self-driving cars develop safe navigation strategies by experiencing millions of simulated driving scenarios. Reinforcement learning allows machines to solve dynamic, unpredictable problems by learning from the consequences of their own actions. AI processes data and recognizes patterns at speeds that human biology cannot match. However, the technology has clear boundaries. Current AI systems lack original creativity, emotional understanding, and self-awareness. Despite the complexity of these algorithms, a machine only knows what its training data reveals. It cannot think outside of the mathematical parameters it has learned. This infographic shows how these learning types have integrated into every sector. The nodes branch out, showing AI managing everything from banking fraud to healthcare diagnoses. These data-driven assistants are currently embedded in our phones, shopping apps, and video games. Recognizing the mechanics behind these three learning types makes the logic of digital interactions visible. Understanding that a recommendation or a blurred photo is the result of pattern matching rather than thinking is the first step in seeing how the modern digital landscape is actually constructed.